In section 3, we are going to talk about how we can describe distributions of graphs, and then we'll talk about our last graph for quantitative data called a box plot. So there are 3 ways you can describe a distribution: by its shape, by its center, and by its spread. And we typically do this after we graph our quantitative variable, so we can identify any patterns or answer any questions we might have about the data. So the first thing we're going to talk about is shape. So once you have graphed your distribution in whichever graph you choose to do, the first thing we do is identify the shape of the graph. So the most common shape we're going to deal with is unimodal. So what that means is that once you've graphed your variable, there is one hump, kind of like a camel. So there's a couple different ways this can look. It can look symmetric, where you've got your one hump in the middle, or your one hump can be kind of off to the side in either direction. So that's going to be the most common type of shape we deal with. You can also have bimodal, which is when you have 2 humps. And those 2 humps can, again, be symmetric, where they're the same height, or you can have it so one hump is bigger than the other. Okay. The last one is uniform, and we're not going to deal a lot with any uniform graphs, any graphs, mainly because they're not very common. So it's when all heights are approximately the same. So typically this is something you can see with a histogram. So you graph it and your graph is pretty much the same all the way across. Very little difference in the heights. They don't have to be exactly the same. It does say approximately, so there could be a little variation, but for the most part, they're all the same. The most important ones that we are going to deal with for shape are the symmetric, left skewed, and right skewed. Symmetric is your ideal graph. So ideally, we want our graph to be symmetric. So that's your bell curve. It's probably a term you've heard before. You have it's unimodal, your distribution is even on the ends, and then you have most of your data in the middle. Technically, bimodal can be symmetric as well, but we're not really going to deal a lot with any bimodal. Then there's left skewed and right skewed, which can be a little bit confusing from their definition. So a graph is left skewed if the tail is on the left. So when we talk about the tail of a graph, we're talking about the lower part. So this part is the tail. So it's where there's the least amount of data. Then right skewed would then be the opposite, when the tail is on the right. So left skewed and right skewed seem a little bit backwards, because you'd think you'd be looking at where your hump is, and that determines left skewed and right skewed, and it's actually not. You're looking for where the tail is, and that determines whether something is left skewed or right skewed. We are typically going to be using one word to describe the shape of a distribution, but in some instances 2 words might be useful. Like if I wanted to draw a symmetric bimodal distribution, so I know it's going to have 2 humps, and those 2 humps are symmetric, which means they're about the same height. Whereas if I'm looking at a unimodal right skewed distribution, that's pretty much the exact same thing as the example we just did. You've got your tail. Sorry, wrong. See, I did the wrong one. Your tail is on the right with your hump on the left. Next, we're going to talk about outliers, which is not necessarily something we will always have for a distribution. It's something that we identify to kind of help explain it. So an outlier, by definition, it doesn't have to be an individual piece of data. You could have multiple pieces of data, but they fall outside the overall pattern of the distribution. And we will talk about how to mathematically identify a value as an outlier, because sometimes a value you may think is obviously an outlier may not be. Other times, something that you may not consider to be an outlier actually is. So we also always like to figure out why you have an outlier. A lot of times, it's just a mistake. You may have typed a number in incorrectly, or if you were gathering data, you could have written it incorrectly. So this is why we always graph our data first, because it's easier to visualize whether an outlier exists than it is to just look at a list of data. So it's not always easy if you're not doing it mathematically, if you're trying to do it just by looking at your graph, to determine whether or not to eliminate an outlier. And depending on who you ask, they may have different rules that they follow on whether or not they get rid of an outlier. So a couple things we typically will always do is, before we even decide if there's an outlier, we're going to graph the data. And then we look to see if there's an outlier. And if there is, we always double check our data first. Then we figure out, is there a valid reason for us to remove the outlier? And we'll talk about that here in a second, of whether or not a potential valid reason to eliminate an outlier. And if there isn't, you don't remove the outlier, you just identify a value as an outlier. So the next way we describe a distribution is with center. And there are 3 measures of center in statistics: mean, median, and mode. Just review: mean is average, median is middle, and mode is most. And we're going to talk about, refresh on how to calculate each of these, and then talk about when one of them is better to use in some situations than others. So what I did here is I collected data from a class on how many siblings, step and half included, a class has, and I copied it down below. So we have anywhere between 0, and you do see there is someone with 11 siblings. So average is a term you've probably heard before to represent finding the mean. It is a generic term for a measure of center, so we aren't typically going to use the word average, because average could mean mean or median. Like, it's very generic. So when you are saying average, you're usually referring to the mean. So we're going to start using mean. We're not really going to say average. So calculating mean in statistics, the formula is x bar equals, and then you have a fraction. The numerator is the summation of xi over n. And I am going to talk about what each of these mean. So x bar is the symbol we use to indicate mean. You're going to see it a lot, so it is something you want to get used to. X sub I represents each individual observation, and that is the subscript. So technically, I could label every number that I have in my table here, x1, x2, x3, x4, all the way up to x25. N is our number of observations, also referred to as sample size. when we get later. And then lastly is the Greek letter sigma, which means to add up. It means to sum. So basically that formula is just taking the words for how we calculated mean and putting it into a formula. So instead of saying add up all the numbers and divide by your sample size, we now have a mathematical formula for those instructions. So when I add up all of my numbers and divide by 25, I get 2.24. So the average number of siblings for this class is 2.24 siblings. It is okay to have a decimal. Put my units here so I know what I'm talking about. You're not always going to get a nice number for mean. So we are going to leave it as a decimal. Okay. So mean is not always going to be the best way to calculate the center of our data. And one of the reasons we don't always use mean has to do with the fact that you include outliers in your data set. So for example, we suppose a student took 7 exams over the course of a year and had the scores of 90, 92, 94, 96, 86, 88, and 0. Now clearly 0 is an outlier here. I don't have to know the mathematical formula or even to graph it really to notice 0 is very, very different than the rest of these numbers. And there might be a legitimate reason to eliminate the outlier. And probably the most common one that people think of here is that the student was absent. And hasn't taken the test yet. So obviously, if they were absent and haven't taken it yet, then their score is going to be a 0 until they do so. So does that 0 accurately tell us how well they're doing in the class? So if we did not eliminate the outlier or cannot eliminate it, maybe they actually did get a 0 on their last test, we would calculate the mean to be 78.29. If I took out the 0 and recalculated the mean, I would get 91.33. So we can see huge difference in our means if we include versus eliminate the outlier. So the outlier in this case is bringing down the mean. Now, outliers can obviously work in the opposite direction as well. If I had a lot of low data and I had one really large value, it could bring the mean up. So the mean is something that we call non-resistant, which means it's strongly influenced by extreme values. So if you do have extreme values in a data set, which may or may not be outliers, that's the other thing is, they may be a lot different than the rest of the data set, but they might not technically be outliers. The mean is not reliable as a measure of center. So when that happens, we like to use median because median is resistant because the extreme values will not be as affected by it. And the reason is when you calculate median, you put the data in order, then you start eliminating it at the ends, working your way into the middle. So the first thing that gets eliminated in calculating the median are those extreme values, whether or not they are outliers or aren't. So what we're going to do here is we're going to reorder our data for a number of siblings, and we're going to put it in order from lowest to highest. Okay. So I went ahead, paused the video, and I copied all the numbers down. So there were 2 zeros, 11 ones, 6 twos, 2 threes, a 4, a 5, a 7, and an 11. So just to refresh, our mean was 2.54 when we calculated it. So for our median, I'm now going to start crossing off values starting at the ends. And you don't want to just do all of one side then all of the other. You do need to alternate which sides you are eliminating data from. So eliminate all my numbers and I end up with one number left, which means my median is 1. So if I'm comparing these values, my mean is greater than my median. And this is probably because we have a person with 7 siblings and a person with 11 siblings. So those really pull up the mean to be a lot higher. Another thing is we have an odd set of values in our data set here. There are 25 numbers, which means when I calculate median, there should be only one number left in the middle. We're going to look at an example later where we have an even set of numbers. And when that happens, you're left with 2 numbers. And if they're the same, then that's the median. But if they're not the same, you find the middle of those 2 numbers by adding them together and dividing by 2. We're also going to take a look at our exam score example. I've reordered the numbers here, so they're in order from lowest to highest. Our mean was 78.29. Calculate the median, and we get 90. So in this case, the mean is less than the median. Now, if I had gotten rid of the outlier and calculated the mean, it would have been a lot closer to my median, which wouldn't have been 90, it would have been 91 because I would have only had 6 numbers, but 91.33 and 91 are pretty much the same number when we're talking about finding mean and median. So they would have been a lot closer if I wouldn't have included the outlier. So looking at these examples, it does not say that the median is always a better measure of center. But whenever you have extreme values that may or may not be outliers, sometimes they are, sometimes they aren't, the median is the better measure of center. Also, there is no special formula or math symbol for median. There's really no formula to say put them all in order, then cross them off and find the middle. And there's no special symbol either. So the last one we haven't talked about is the one that we are never going to use to identify the center of a distribution, and that's the mode. Because it identifies the most occurring value in the data set, and that value that's the most occurring may not necessarily be anywhere near the middle or the average of your data set. So it's not really a helpful measure. We'll never use mode to identify the center of a distribution. We'll always be using either mean or median. So let's take a look at some examples to kind of help us determine when do we want to use mean, when do we want to use median. So I have 3 sets of data here, and what I'm going to do is I'm going to create some really rough histograms. We're going to calculate the mean, median, and mode, and then we're going to talk about the shape of each of those distributions. So for my first set of data here, I'm going to do 70, 80, 90, 100, 110. And I'm going to have my y-axis go up by ones. So I'm going to go 1 to 4. So there are 2 numbers between 70 and 79. There are 3 numbers between 80 and 89. I have 1 number between 90 and 100. And I have one number between 100 and 109, and that's 100. The easiest one to find first is our mode, which is 80. When it comes to finding the median, there's an odd number of data, so it ends up being 80. And then if I calculate the mean, I'm going to get 84.7. Next, I'm going to talk about the shape of my distribution. So sometimes I find it easier, especially if we're dealing with a histogram, is to draw a curve based on my graph. So I'm going to go up, then I'm going to come down with my data set. I'm going to start. There we go. So if I look at the general shape of what I get something that's kind of symmetric. It's not like perfectly symmetric, so I'm going to call the shape roughly symmetric. It does not have to be 100% perfect, like yes, this is definitely a symmetric distribution. You can say something is roughly symmetric. It's not exactly left skewed or right skewed. It's not obviously skewed in either direction, and that's when we say something is roughly symmetric. Second set of data, I'm going to again do the same scale, 70, 80, 90, 100, and then 110. I'm going to go from 1 to 4. I have 4 numbers between 70 and 79. I have 1 number between 80 and 89. No numbers between 90 and 100, and then I have my 1 number between 100 and 109. So this time my mode is 77. There are only 6 numbers in my data set, and when I start crossing them off, I end up with 78 and 79 left, which means my median is going to be 78.5, which is directly in the middle between 78 and 79. And when I calculate the mean, I'm going to get 82.7. When it comes to the shape, so if I'm looking, I have up and then it kind of levels down to the low values. So this is a great example of something that is right skewed. So if we're going to identify something as left skewed or right skewed, you want it to be pretty obvious that it's skewed in a direction. We don't want something where you're kind of guessing or you're not sure if it's skewed in a direction. Then our last example, I only have to go 70, 80, 90, 100. Also going to go from 1 to 4. So I have 2 numbers between 70 and 79. Also 2 between 80 and 89. And then I have 3 between 90 and 99. Okay. My mode is going to be 73. My median is going to be 89. And then our mean is going to be 86.3. When looking at the shape, it starts off low, then it goes up. So this is going to be an example of left skewed. So doing these examples, we're going to compare our mean and our median and look at the shape of that distribution and kind of get an idea of the relationship between the mean and median to help us determine when we want to use each. The first one is our symmetric distribution. So when we're dealing with a symmetric distribution, in the middle here, our mean and our median, and even our mode, should be approximately the same. So that's what these symbols mean, is approximately. They do not have to be the exact number, but they should be fairly close to each other. So that's why the first example we did here, I call it something that's roughly symmetric. Our mean and our median are identical. They're pretty similar to each other. Our mean is a little bit high, which is why I wouldn't say that it's symmetric. I say roughly symmetric. It's close, but it could be closer. Next, we're going to look at something, our left skewed. So when we're dealing with left skewed, okay, our median in both left skewed and right skewed should be closer to where our hump is. So this is where our median should follow. And then because in a left skewed distribution, most of your values are at the higher end, it actually pulls the mean down. Because the few lower values you do have, so if you look at the last example we did, the mean, because we have a lot of lower values, pulled that mean down. So in this case, our mean is less than our median. Our median is going to fall where most of the data is. And then lastly, we have right skewed. Okay. So again, our median is going to fall closer to where the hump is, but our mean is going to follow those few extreme values. So in this case, our mean is going to be greater than our median. So that's what happened in our second example. So if you're looking at a graph that is obviously left skewed or right skewed, we're going to want to use the median as our measure of the center. If there's something that's symmetric, we have a choice between mean and median, but we're typically going to go with mean. Just because mean is a little bit more accurate. You're not necessarily going to get the exact same number for mean and median, but the mean might be a tad bit more accurate if something is symmetric. So the last type of descriptor we use for a graph is the spread. And spread there are also 3 common measures of spread in statistics, one of which you've probably heard before, and that's range. Okay. We are going to define range a little bit differently than what you may have seen in the past. The next one is standard deviation, which is going to be a very important calculation in statistics this year. And the last one is called IQR, which is an abbreviation, and I'll get to that later. So for right now, IQR. So the first one, we're going to talk about range. So in statistics, range is calculated as a difference. So you take your max value, you subtract your minimum value, and that's going to equal your range. So in statistics, range is a number, it's not an interval. So if I have a set of data that goes from 45 to 67, I'm not going to say my range is 45 to 67. I'm going to say my range is 22. So it's that difference. Okay. We do not use range a whole lot, just because saying that my range is 22 doesn't really give me a good indicator about the distribution. It's like, oh, so the range is 22, but are those numbers closer to the lower end? Are they closer to the higher end? Are they closer to the mean? So there's not really a lot you can get from range. One of the most common ways we talk about the spread of a distribution is the standard deviation. So standard deviation is the average deviation or average distance of an observation from the mean of the data set. All right, and instead of just giving you the formula and then doing an example after that, we are going to do an example where I talk about each of the steps as we're going along. So for example here, a group of elementary school children were asked how many pets they have, and we have their responses arranged from highest to lowest. It's not necessary to arrange your values from lowest to highest when calculating standard deviation, but We have it here. So the first thing you have to do in calculating standard deviation is find the mean. So if I add all these up, and then n is going to be 9, because there were 9 kids, I get a mean of 5. It is also not going to be the case where your mean is a nice number, a nice whole number like this, but just to make the process a little bit easier for the first time, the mean is nice. So the first step in calculating standard deviation is to subtract the mean from each of your observations. And it is important here that you're subtracting the mean from the observations and not the other way around. For whole numbers, it doesn't really affect the answer, but considering most of the time that you guys are going to be calculating standard deviation, your mean is going to be a decimal, it does matter for that. While we're not going to do standard deviation by hand all of the time, you will be asked to do it some of the time. So it is important that you know the steps. So if I do 1 minus 5, I get negative 4. 3 minus 5 is negative 2. 4 minus 5 is negative 1. 5 minus 5 is 0. Then I get 2, 3, 4. Now I'm going to square each of these deviations. And whenever I square a negative number, I do get a positive number. So I'm going to get 16, 4, 1, 1, 1, 0, 4, 9, 16. And the reason why we square the deviations is if we go back to the definition, it's the average distance. I know it says deviation, but deviation can also means distance of an observation from the mean. And if we're talking about distance, distance is a positive number. So we don't want, nor can we have negatives when we're calculating average distance. So that's why we square our deviations so that we're getting rid of that negative. So we're no longer paying attention to whether or not our distances are above or below the mean. We just have a distance. The next step in calculating standard deviation is to find the average squared deviation. So the first step is to add all of those squared deviations together. So we're going to get 52. So depending on what you do next, changes whether or not you're finding sample standard deviation or population standard deviation. And most of the time, we are going to be calculating sample standard deviation because we're going to have a sample of data. We're not going to have every value from the population. So for sample standard deviation, to find that average squared deviation, we divide by n minus 1. If I were finding population standard deviation, I would be dividing by 1. And dividing by n. And I'm not going to go into the reason because it's calculus. So we're going to take 52. Because there were 9, I'm going to divide it by 8. So the next value we get, 6.5, is called the variance, which is the average squared deviation of the number of pets for this group of elementary children. Variance is not really useful because not many times we say, oh, what's your average squared deviation? We don't really ask for that information. And then because it is average squared deviation, the units are technically squared pets, and that's useless. Like, why would you have squared pets? So in order to get our correct unit, which is just pets, we take the square root. So my variance is 6.5. So I take the square root of 6.5, and that gives me my standard deviation, which is 2.55 pets. So that tells me that the average deviation from the mean number of pets is 2.55 pets. So now let's put all of this in a formula. So the symbol for variance is s sub x squared, and then equals my numerator is the sum of the squared difference between the mean and each individual observation divided by n minus 1. So it's not a very nice looking formula, but as long as you understand the steps, you don't really need to have the formula memorized. So S sub x squared is the symbol for variance. X bar is still mean, x sub I is still our each individual observation, n is the number of observations, capital sigma means add up. So the difference between the standard deviation formula and our variance formula is that we take the square root. So then the symbol for standard deviation, which is very important, is S sub x, and then the square root, and then our variance formula, summation of x sub I minus x bar squared over n minus 1. Again, you do not have to memorize this as long as you know the steps associated with calculating variance and standard deviation. So a couple things about standard deviation. So if I'm going to interpret the standard deviation in context, which is a very important piece about standard deviation, is being able to interpret that in the context of your situation. I would say the number of pets typically varies from the mean by 2.55 pets. So I want to have my units. Now, is that a high number? Is that a low number? Is that good? Is that bad? It really depends on what your mean is. So in this case, my mean was 5. So the average number, so the mean of our data set was 5 pets. The larger the standard deviation, and we're talking about here this in the second, the larger the spread in the data. It means that there's more variation in your data. So the smaller the standard deviation in relation to your mean, the better it is. So 2.55 is pretty large considering our mean is only 5. So I wouldn't say that we have a small spread. We have fairly large spread in our distribution here. Now, if the mean was 1.1 or even 0.75, I would say small spread, because again, comparing it to the mean. If my mean were 45 and my standard deviation was 2.55, I'd say that's a pretty low standard deviation. So again, standard deviation is low or high based on whatever your mean is in the context of your problem. So standard deviation measures typical distance of the values in a distribution from the mean. That's a very important thing here, is we're talking about distance from the mean, not distance from each other, just distance from the mean. So because we calculate standard deviation using mean and its interpretation is based off mean, we will only use standard deviation as the measure of spread if you use mean as your chosen measure of the center. So we typically only use standard deviation if the data is symmetric, because that's when we prefer to use the mean. Couple other things about standard deviation. It is always positive, all right, because it is distance. Can't have negative distance, so it is always positive. You can get a standard deviation of 0, and that specifically happens when all observations are the same. So obviously, if I have a set of data that's all 2, my mean is going to be 2, which means the typical distance each value is from the mean is going to be 0 because it's 2, and all the numbers are 2. So can get 0, but only in one specific case. Standard deviation has the same units as the original variable. So we found the average number of pets. We found our mean number of pets. My standard deviation units are also pets. And then similar, because we use mean in calculating standard deviation, it is non-resistant just like the mean, which means it is heavily influenced by extreme values or outliers. So depending on if that outlier is a higher or lower values, it can make the standard deviation larger or smaller, which is the reason why we don't use standard deviation when we have outliers, because it is influenced by those outliers. So I kind of already mentioned this, the greater the standard deviation, the greater the variation in your distribution. So we typically want smaller standard deviations. So the last measure of spread is something called IQR. And IQR stands for interquartile range. And IQR is specifically used when with percentiles to describe the spread of the distribution. So just kind of refresh, percentiles measure the percent of the observations that fall below a value. So if the median is the middle, where 50% is above and 50% is below, the percentile it would represent is your 50th percentile. So median goes closely with percentiles. Some other percentiles. This will be the only time you hear me say it. 0th percentile, also known as your minimum, because it is the lowest value in your data set. Nothing falls below it. It is the lowest you can get. 25th percentile is also known as quartile 1. The first quartile. Also known as Q1. And it says 25% of the data is below this value. Your 50th percentile, what we just said is the median, is your middle. Then you have your third quartile. So quartile, you kind of think about it, it is splitting stuff in fourths. So your first fourth is 25%, your second fourth is 50th, your third fourth is 75th, also known as Q3. 75% of your data is below this value. And then lastly, the 100th percentile is your max. It is the highest value in the data set. Now, in statistics, they don't use 100th percentile. They only go to 99th percentile because there could potentially be someone who gets something higher. So at this point, the 99th percentile, no one has gotten anything higher than you, does not necessarily mean it's not possible. It's not the biggest possible number you can get. It's just the biggest number that's gotten so far. So 100th percentile, not really used a whole lot in statistics, but for our purposes, because we'll have a minimum and a maximum, we'll use 100th percentile. So these 5 numbers are minimum, quartile 1, medium, quartile 3, and max. There are 5 numbers there. They make up something called the 5-number summary. So we are going to talk about how to calculate them by hand, but we're also going to then discuss how to do most of the calculations we've talked about in these notes, except for median, using the calculator as well. Because these can all get very time-consuming to do by hand, especially if you have larger sets of data. Also, to calculate your 5-number summary by hand, because you have to do median and it talks about middle, your data has to be in numerical order. And if it's not already in numerical order, it's added more time consuming to put it in that numerical order. So we have a set of data here for our example where previous stats class were asked how many hours of sleep they got before the first day of school. And we range anywhere from 2 to 8.5 hours. So the easiest 2 things to identify first are your min and your max because they're already in order. 2 is my min, my max is 8.5. I cannot calculate quartile 1 or quartile 3 until after I've calculated the median because they talk about the lower 25% and the higher 25%. Until I know where that 50th percentile is, what marks the middle, I can't find the lower and higher 25%. So I'm going to start by finding my median. So start crossing off numbers at the ends. and I end up with 2 7s. And the middle of 7 is 7. So that's my median, 7. Next, I want to find the first quartile, which is the median of my bottom half. So I do have to technically split up those 2 7s that are left, and one of them gets included as the lower half of the data, and one of them gets included in the upper half of the data. So now I calculate the median again, and I start crossing off numbers. And I end up with 6. So 6 is quartile 1. And I do the same thing for my upper half. And we get 8 for quartile 3. I now have my 5-number summary. I know my minimum, I know my maximum, I know each of my quartiles, and I know my median. Now I can calculate my interquartile range. So the interquartile range is the range for the middle 50%. So what that means is you take quartile 3 and you subtract quartile 1 from it, and you find the range between your middle 50% of the data. So just like range, it is a single number. It is not an interval. So for us, our quartile 3 is 8 minus quartile 1 is 2. So my interquartile range is 2. So there's a 2 hours difference between my lower and upper quartile. So the middle 50% of my data is only differs by 2 hours. Last thing we're going to talk about is our box plots. So box plots is the last type of graph that we can use to display quantitative data, and it is specifically created from our 5-number summary. So it's specific to percentiles. So when you are creating your box plot, it's very similar to how a dot plot starts. So you have an x-axis, and you label that x-axis, which in this case is hours of sleep. You then are going to have a scale. So my minimum is 2, and I don't want to go up by 0.5s because most of my numbers are whole numbers. So I'm going to go up by 1s. So 2, 3, 4, 5, 6, 7, 8, 9. And then if I have to do a 0.5, it would just fall in the middle between a number. So my minimum, it gets plotted with a point. Then my box is comprised of the first quartile to the third quartile, and I also label my median, and then I end with another dot at my max. And then I connect my box to my minimum and my maximum with lines. And those are technically called whiskers. So I have my minimum, quartile 1, median, quartile 3, and my max. You do not have to label them in the graph. I'm labeling them so you know what piece is for each of the graph. But when a box plot is graphed, that's the way people interpret it. They know that that first value is your minimum. The first line in your box is quartile 1. The median is that middle line. Quartile 3 is the end, and the max is the last. So we've talked about outliers so far. We've talked about how to kind of look at the graph to see an outlier, but there is a mathematical test using our IQR and our quartiles that allows us to determine if there is an outlier or not. So it's called the outlier test. So anything below a certain value from your first quartile or above a certain distance from your third quartile is considered an outlier. So anything 1.5 times the IQR below or above your first and third quartiles is considered an outlier. Don't ask me where the 1.5 came from. I don't know. So if we're using our sleep example, If we do quartile 1 minus 1.5 times the IQR, quartile 1 was 6 minus 1.5 times 2, which is 6 minus 3, which gives us 3. So anything less than 3 would be considered an outlier. I'm also going to check anything 1.5 times above 1.5 times the IQR above quartile 3. So that's 8 plus 1.5 times 2, which is 8 plus 3, which is 11. So then I'm also looking for anything greater than 11. There is a value less than 3. My minimum is 2. There are no numbers greater than 11. So 2 is the only outlier. So 2 is an outlier. So this is one of those examples where I wouldn't necessarily automatically think there's an outlier here. I wouldn't just looking at the set of data say 2 is an outlier. Just because it's not a huge range here. My range is only 7. It's a pretty small range. You wouldn't normally think, oh, there's an outlier here. But considering most of the numbers are higher numbers, 2 does end up being an outlier. So the nice thing about box plots is you can create a box plot that identifies the outliers, and you can kind of look at the box plot in a modified way to identify your outliers and see kind of a better distribution of that. So to create a modified box plot, it starts off the same as a regular box plot. You're going to have your x-axis and your label, so hours of sleep. My scale is going to be the same, 2, 3, 4, 5, 6, 7, 8, 9. But this time, instead of putting a dot at 2, I'm going to put an asterisk, because that indicates that 2 is an outlier. And my new minimum is my next smallest number, which in this case is 4. The rest of the box plot is the same. I have quartile 1 at 6, quartile 3 at 8, my median at 7, and then my max at 8.5. So now my whisker on the left between my new lowest value and my first quartile is a lot shorter than it was on my regular box plot. Let me know if you have any questions about how we describe a distribution, whether that's with shape, center, spread, calculating outliers, the 5-number summary, or creating a box plot.